the main important aspect is that in a system today, in a multi-processing system, there are multiple processes, all of them need to execute, and we have say one CPU, right, on which these processes can basically execute one after another, and there is an operating system routine or part of the operating system routine which is called process management, which will be responsible for assigning the process to the CPU. The process management is actually responsible for taking, say, this process will execute on the CPU at this point of time, right. So, as we had instruction scheduling, we also have something called process scheduling. Okay, right, and importantly, so essentially the processes can be in 3 stages. A process, the moment I type ./a.out, it comes and sits in a queue which is called a process queue. So, the process in what is in a state called ready state, right, it is ready for execution, right. Then your scheduling algorithm, or what we call as a scheduler, will schedule it, then it goes to a running state, right. If there is an interrupt, it comes back to the. So, what is an interrupt? Exceptions are of 2 types, interrupts and traps. Interrupts are those that are given by an external input, while trap is something that is given by the process itself. So, if it goes to if it gets an interrupt, it goes back to the ready state, while if it executes a trap, then it goes to a suspended state, and then on wake up it basically comes back to the ready state. For example, if I want to do a printf, okay, I go to the suspended state because the printf is going to be executed by the operating system. Printf is a routine which is to be executed by the operating system, right, or malloc is a routine that is going to be executed by the operating system. So, that type of a thing, this trap, we call it as a system call. If I execute a system call, then what happens? I as a process will go to a suspended state, the operating system will start executing, it will finish it, after finishing it will wake me up and I go again to the ready state, and again I should get scheduled to start running. Are you able to understand this? And at some point of time on running or in suspended state, I may have what you call as termination. I go to a terminated state. Okay. So, this is basically, so the process can be in 4 states, it can be in a ready state, it can be in a running state, it can be suspended, it can be terminated, right. Are you able to follow, right? So, scheduler is an operating system part. When I do a trap, the system call is also part of the operating system, right. When the process completes, again this termination is done by the operating system, okay. So, the termination also is done by the operating system. What do you mean by terminating a process? Now that you have understood lot of computer organization, what are the steps involved in terminating a process? I have to free the memory, I have to free all the resources allocated, etc., etc. Basically freeing of the memory and then the all the informations that are necessary for this. So this is how a multiprocess system works. So this is called what? This is called what we call as a state machine. So I am using a state machine to describe the different states of a process. Okay. You will see several state machines when you want to describe different aspects of your architecture, operating system, software, database, everywhere you will see state machine. So what is this state machine? You have learned now automata theory, right, to some extent. So what is this state machine called? Deterministic finite state automation. So in the operating system course that you are going to do next semester, you will go more in depth into how this state machine is processed, right. The role of the, so one of the important functionality of the operating system is process management. And what do you mean by process management? For every process I should go and fix which state it should be. Every process has its own state machine, it has its own state information. So all the process in this queue will be in ready state, all the process that is executing on the CPU will be in running state, and some process waiting on the IO queue or something like that, right, for doing the IO, that will be in suspended state, and so on and so forth. So how do I manage the state transition of each of these processes? Essentially constitute what you call as process management. So when you start your operating system course, you will learn about process management in great depth, right. Now what we will do now is, what are the underlying architecture features that will enable you to do process management? Are you able to get this? What are the underlying architecture features that will enable you to do process management? And that is what we are trying to do. So already you have seen segmentation, you have also seen, you have been exposed to interrupt service routine. So now since you have understood how interrupt service routine works, interrupt descriptor table register that will point to a start of an IDT, and there are entries 0, 1, 2 till 255 in this. Now every hardware trap will be assigned a number. So you go to this number, and in this number what will be stored? There will be a segment selector, right, and an offset. Then there will also be a privilege level. Okay. So this is called, basically this is called an interrupt gate. There is some small difference, interrupt gates / trap gate. Okay. In this I can also put something called a task state segment selector, TSS selector, or what you call as, sorry, I can call it as task gate. We will deal about it later. Okay. There is also a thing that we can put a task gate here. So currently what you are going to, in your GDT, what did you put? We put normal segment selectors for data and code. Here I am going to put segment selector or segment descriptor for interrupt, right? And that will basically have a segment selector. Now where is the segment selector stored? It can be stored in GDT, right? It can be stored in GDT or LDT. Now, so basically now from there you go there, and there what will you get? The base address. To that base you will add this offset, check for the limit and start executing from there. This is what the hardware supports. Didn't you read this? Are you in the class or not? Okay. So how do you fill up this IDTR? Using the instruction LIDT. And this LIDT is what? It's a privilege instruction. So only the 0 level can set up an interrupt descriptor table, right? Okay. So this is the entire setup about IDTs. So this is the setup about interrupt. I hope you all know everything about segmentation now. Segment descriptor, privilege level, limit, etc. Okay. Now let me talk of some couple of scenarios. So architectural enhancements to improve performance, right. So this is one thing that we need to look at from segmentation. So this is something more than what you have studied. Maybe you have studied this, let me just find out. So what happens if I say move some 0x 555 comma ex? What should happen now? What are the steps involved in doing this? First thing is there is a DS register. The DS register will have some value, let me say 0xv. I go to that corresponding entry in the GDT. There is a GDTR which points to the basis of this. I add this and basically get to this entry. Here what I am going to see, I am going to see the base and limit. I take the base from here and I do base plus 0x555. I also check the limit 555 with this limit, and if it is more, then I say a segmentation fault, otherwise I continue here. So then what? This gives me, let the base be some 0x1000, then it gives me 0x1555. This again I go to the memory 0x1555, I access and bring it back. So what one memory access essentially means going to the GDT, which is, where is the GDT stored? Also in the memory, and then getting the base and limit, checking it, and then calculating. So this address is what? This is logical address, okay, and this address is actually physical address, or what we call as effective address. Correct? Once I calculate the effective address, again I go, again I fetch. So one memory fetch actually became what? Today now it has become two memory fetches. One memory fetch essentially became two memory fetches. Correct? Correct? Now how do you solve this problem? Now in a DS register there will be a selector, then this is visible, then there is some invisible part which will be the base and limit. This is the invisible part. So nobody can actually go, the user cannot go and change. Now what happens, let us say this is the GDT and there is some say 0x10 entry, okay. Now when I say move and let it as base as 1000, limit as some 55 and some, okay. When I say move ds comma 0x10, what happens? Actually I can't say 0, move some ax, move ax comma 0x10, okay. Always you do like this, right? So when I say move ax comma 0x10, what will happen? And move ds comma ax, what will happen? 0x10 gets stored here, 1000 gets stored here and 55 gets stored here. But this is a shadow part. This is called the shadow register. So when I say move 0x555 comma say some 0x10 or whatever, this 555 is added to the base that is stored in the shadow register. I need not go to the memory. So I will just add to this base whatever, this is be 5555, whatever. I just add to this base in the shadow part, right, instead of going to the memory. So whenever I am updating the DS register, the selector gets stored in the DS register. In addition, my base and limit as stored in the GDT or LDT is stored here. So whenever I want to calculate say like instructions like this, I need not actually go to the memory to find out that the base is 1000. That will be available in the shadow register itself. So the two memory accesses actually became one memory access. correct. Now what is the drawback of this? So suppose I want to increase the size of this segment. This segment has grown, I want to increase it, so append more memory. So I want to raise the limit from 5555 to some 8888, okay. Now what I will go and change in this location. How will I change in this location? I will use normal move whatever GDT let it be some 1000. So I will use normal move to basically go and change this location. So I can go and change this as 8888. This is I am only touching the memory. That 8888 will not get, how will it get reflected here? It will not. Because I am only changing the memory, I can go and change memory in any way I want, right. This in normal memory operations like move I used to go and change this. When it gets updated here in the GDT, how will it immediately get updated? It will not get updated. So even though this has become 8888, if I take selector 10 and I look at the base limit, it is still 8888, but the shadow part will still retain 0x5555, right. So the moment I go and change the limit, again I should re-execute these two instructions to see that this 5555 is replaced by 8888. So whenever I go and change the base or limit of my descriptor, I now go and do move ax comma that descriptor, move ds comma ax. I go and do it so that whatever change I have done to the base and limit or privilege level essentially gets updated here also, okay. So what is this problem called? Some value in the shadow register and some other value in the GDT. What is this problem called? I have talked about this in earlier class. There is a coherency issue. This is not cache anyway. So there is a coherency issue, right. The data is not consistent, data is not coherent. So there is a coherency issue. For all practical purpose, the shadow register is basically a cache of your right, cache of what? Cache of your GDT entry. So this basically leads to a cache coherency issue. So every time you go and expand a segment, you need to go and reload your DS, right. Unless it is documented, you will not know what is happening, correct. You always feel that if I go and change in the segment descriptor table in the GDTR, if I go and change the limit or anything, this will work, but it will not work, right. Able to follow? Any other doubts? Operating system has to check for all. Operating system has to check for all.
Which all?
Who are all? It will know who are all the segments for a current process. It will know who are all the segments, who are all the fellows that are using it. So it has to do it for all these fellows. In the case of task switching, it is automatically taken care of. I will tell you how it is happening in the 4th programming assignment post. So after ISR, we have to do paging, okay, and then we have to do task switching. So 2 more assignments are there, 2 more solid assignments are there. Okay. Next, yeah.
The total number of entries in the GDT. So you said in the video that it would be only 256.
0 to 255 I thought. Okay, yeah, tell me.
But since the segment selector we have 30-bit index for the entry in the segment descriptor for the GDT. So there can be 8192 entries.
There can be 8192 entries, but somebody has to map it, no? See, this is not, see, when an interrupt comes, it is the hardware that is mapping that to a entry in the IDT. The maximum interrupt that the hardware, see, who is doing this? There is an hardware which realizes that there is what do you say, there is a interrupt. It takes that number and then it goes to the interrupt descriptor table and say, okay, start executing this. So that hardware has to realize this number and then take that number to the IDT and index there, and that realization it can do only up to 256 entries. You are getting this. It is not like normal addressing.
I am asking for GDT.
What GDT?
Global descriptor.
Ah,
The total number of descriptors in the GDT,
ah.
how much they can be.
Number of descriptors in a GDT. So this is 16 bit, and in this 16 bit we are removing the so 16 or 12 bit. So what is 2 power 13? We can have up to 8192 descriptors. I said 255 only for the interrupt descriptor table, not in the GDTR, right? So yeah, this is 255 only for the interrupt descriptor table, not for the GDT. GDT I can go whatever I want. The only one thing that you need to confirm in the LGDT statement, you basically store the base and limit of the descriptor. When I do the LGDT of some address, and in that address I will store the limit and base of the descriptor. I don't know what is the size of this limit. I think that is 68 bits, no. Maybe 8 bits. I will go to Intel manual and then find out. Yeah, so this basically, yeah. So as you see here, I am just moving the cursor, my hand, oh shit. Yeah. This has a 16 bit limit. So it has a 16 bit limit. If operand size attribute is studied with 16 is 6 byte memory location that contains the base address and the limit. Okay. Yeah, it's a 6 byte. So 2 bytes are available. So this is 16 bits, and the limit size, a linear address and the limit, that is 4 plus 2, 6 bytes. Okay. So 2 bytes is 16 bit. 16 bit means I can have 8192 entries. Yes. Because I can have 13 8 bit, no? Okay, so that's the limit. You can have 8192 entries, yes. Except that you may go mad if you have such many entries. That's different.